So when a customer comes to me, they say, Rob, they start crying a little bit, Rob, I'm upset. Rob, my builds are too slow. I'm running too many automated tests. They're too slow. We have too many automated tests. Then I go to them, I stand up tall, and I hug them. Big hug. And in Canada we hug a lot, so big hug. And I say, congratulations. Finally, you have the right problem. That is the problem. I want each and every one of you in this room, I want you to have that problem. I want you to have so many automated tests that your build is too slow. I want you to have that problem. And you're going to get to that problem. And once you get to that problem, that's the right problem. Not all problems are the wrong problems. Slow builds because you're doing too much automated testing. It's a party. Have champagne. This is a special occasion. That's a beautiful problem. That's the right problem. And I look at that and say, fantastic, finally we have the right problem. Let's fix it. And there's at least 3 strategies we can use to fix it. Got that on film. I just want to make sure it's on. We're filming the, there we go. It's coming. Oh, it's going to be a little one in the corner. Is it going to be a little one? Yeah! This is so cute. The little thing in the corner. And I tell them, no, they make me work when I come to Malaysia. It's not just a big party. Okay, so fast builds, we have some strategies to make them faster. And the last one is accessible builds. They're builds that we have to be able to identify. Think about this. In a waterfall project, what happens if you test the wrong build? Well, you go and you tell the developer and you change the build and you start testing the right build and you maybe waste a little time. If you have an Agile sprint that's 2 weeks long, and you spend 2 days testing the wrong build, you wasted 20% of your time in the sprint. Therefore, an accessible build, you have to be able to identify what build am I testing, what code is in that build, what stories are in that build. So to give you the idea, frequent builds, okay, there's 3 styles. Periodic, you do it every hour or every day, periodic. There's on demand, that's whenever someone checks in code, you do builds right away. And there's continuous. When one build finishes, the next build starts. So that's strategies for it, but always we have frequent builds. Automated, yes. Tied in, whenever the builds are self-engaged, they run by themselves. Self-tested builds, this is when we run the smoke test, unit test, and story test automatically on every build. Fast build, if it's too slow, what do? We can do hardware scalability. Almost every modern build system, you can just put more hardware, more memory, more CPU, it'll be faster. However, sometimes all the tests have to be done sequentially. If that's the case, then there's a serious problem. You can't just make hardware scalability. But there's 2 strategies people use, and they've been doing this for years and years. One is called railroading, and one is called shotgunning. In a railroading approach, what we do is we say, okay, our project has 1,000 automated tests. Build 1, we're going to test 1 to 200. Build 2, 201 to 400. Build 3, 401 to 600, etc. until you get to the end, then you start over. So you don't do every test on every build, but after so many builds, you've done all your tests. So that's faster. that's called railroading. You don't do every build on every test, but after so many builds, you've done all your tests. And this is what you see, a nice strategy. But another way, which is even better, it's really cool, it's called shotgun. And in shotgunning, what you do, and what I really like about this, is it randomizes the tests. So you don't do every test on every build, but you randomly select. So let's say you have 1,000 tests. The first build, I randomly take 200 from the 1,000. Then the second build, I randomly take 200 from the remaining 800. And in the third build, I randomly take 200 from the remaining 600. It's random selection without replacement. Sampling without replacement. And after 10 builds, or after so many builds, I've done all the tests. Plus, I avoid, in some ways, the pesticide paradox, because I don't do all the tests in the same order. I randomize the order of the tests, so I can start finding regression bugs related to dependencies. Order dependencies. If you always run the tests in the same order, you'll never find a bug that depends on the order. So randomizing them is actually, it finds more bugs too. So shotgunning. Those are strategies to make it faster. As I said, it's a beautiful problem to have. You give yourself a big hug when you find that problem. Accessibility, I identify the build. I know this is the right build, plus I can check what code was in that build. Is it the code I expected? And what features are implemented, what stories are implemented in that code. So that's accessible builds. Now, when we're doing the build, we have an opportunity to do some static analysis. The term static analysis implies, like everybody was saying, early testing, but also we can do some cool non-functional testing. Static analysis tools are run on the build server. When you're doing the build, they're run, and you run the build, and then you use the tool to look at, usually you look at your source code. So you look at your source code, and you get information about the source code that you built. And this information can tell you about potential problems, potential technical risks. They'll give you interesting warnings. Static analysis tools are widely available today and are very reasonably priced or free. Every March, I work with my students at McGill. We keep a list of static analysis tools, and you'll find a copy of that in the Dropbox, where you get the tool, what the website is, all this type of stuff. There's many available. I try to use as many free ones. The language you're using, the version of the compiler, and the operating system that you're using. You need to get the exact right tool for the environment you're using. Otherwise, you could miss very important bugs. So, what type of things do we use these tools to get? Well, one thing we can do, hello, that went a long time. I was so happy. No? There. So, we can look at size and complexity of our code. Size and complexity. So this room here is a nice example room to work in. If I'm standing here and I want to go to the door in the corner, how many pathways are there through the classroom? There's one big one here, one through the middle, 2, one through the edge, 3. But what if there's looping? What if I went looping around? There's actually an infinite number if I go looping. And don't forget, I know I'm sort of fat, right? But pretend I was skinny. And then I could walk through here. Or I could walk through here. Or I could walk, if I was very skinny, I could walk through here. Or here. And so you have basically, if you think of it, there's a large number of pathways through this classroom. In a piece of software, there are many pathways you can take through a piece of software. Those pathways give you an indication of the complexity of the software. And in software engineering, for many, many years, we've used a method called cyclomatic complexity analysis to study code. Cyclomatic complexity can be computed, lazy, and implemented a construct that I like to call the bozo bit. The bozo bit is a programming structure where someone adds a logical variable, and then every time there's a calculation, they say, if the variable is true, do it this way, otherwise do it that way. If it's true, do it this way, otherwise do it that way. And what they're doing, let's say you, for example, you have software that works in Canada, and you want to sell it in Malaysia, but the rules are different for computing tax in Malaysia. So, in my code, everywhere where there's a calculation, I say, if it's Malaysia, do this. Da, da, da. If it's Malaysia, do this. Da, da, da. If it's Malaysia, do this. If I do that, I've doubled the complexity of the code, and I did no analysis, and I could program it very fast. And it works. It works. I programmed it very fast. But then, we sell a version of the software to China. And now, everywhere there's a calculation, I have to put, if China do this, if China do that, if China do, I mean, we have tons and tons. It's called, that's how you generate spaghetti code. And as you get more languages, you get into linguini. And you get more languages, and we get an Agile hair pasta. And then you're eventually going to get to vermicelli noodles. So with, do you know what I mean? This code is all spaghetti. It's all terrible. So if you have an increase in complexity, again, a tool, automatic tool, is going to give you this number. It's free. They give you this number. You look at the table. Number went from 20 to 40. That is a sign of technical risk. That tells you, that number tells you, you should do some exploratory testing around the features that use this code. That's free. It comes from a tool. That's test automation. It's not doing the testing for you. It's telling you where the technical risk